Okay, so this time we want to talk about the combinatorial structure behind the formulas for freeness, for free variables. We have seen in principle freeness is a rule for calculating joint moments of free random variables out of the moments of the individual random variables, but at the moment the structure of this formula is not clear. Right? And in order to go further, it will be good to have a better understanding of this formula. And there's actually a nice combinatorics behind, which we want to try to understand. So the second chapter is essentially, leading to or motivation for the structure which is in the background. So this is about the emergence of combinatorics of free probability theory, and this motivation will be essentially given by looking on central limit theorems, in particular the free central limit theorem, because this will give us some crucial insight how this combinatorial structure looks like. Okay, and then in the following chapter we will give a more systematic description of this combinatorial theory. So this is more about getting an idea what really are the relevant combinatorial objects and how should we formulate joint moments. So maybe let us first look on the problem. So what is our setting? We have a non-commutative probability space, and we have unitary subalgebras AI indexed by some index at capital I, and we assume they are free. Okay, and then, so this means we have seen that what this really means is that joint moments are determined by the moments of the separate variables, or maybe this means that phi restricted to the algebra generated by the AIs is determined by the phi restricted to the AIs. And maybe it's good to assume without loss of generality, that actually A is equal to the algebra generated by the AIs. Oh, okay. Because we cannot say anything about elements which are not in this algebra. Okay, and then so our main observation was that phi on A, this is determined by the knowledge of phi restricted to the AIs. Okay, but to understand, this is something which we should understand better how it is really determined. So what does this mean? Elements in A are polynomials in elements coming from here. Because everything is linear, it's enough to look on monomials. So this means we are really interested in elements which are products of elements coming from the different subalgebras. So what we are interested in is a product up to k, where k is a natural number, and the factors here are coming from one of the subalgebras. So usually we say aj comes from the subalgebra I with the index I of j. In I of j, those guys are just elements in our index set. So this means the aj's are coming from one of the subalgebras. And if you like, we can also assume that neighbors are coming from different subalgebras, because if not, we can multiply the neighbors together and then they are just another element in this specific subalgebra. Also, usually we can assume I1 is different from I2, and so on, different from IK. Good. Okay, and so what we want to understand is what is phi of such a guy. How can we express this in phi restricted to the variables itself? Okay, the definition of freeness tells us what this is in a very explicit way, in a very specific situation, where we also assume that each of the phi is centered. So if the phi of AI is equal to 0, or let's say aj is equal to 0 for j, then freeness, that's just the definition, tells us that phi of a1 up to ak is equal to 0. Okay, but in general, of course, we don't want to assume that those phi's are centered. No? We have seen we can reduce everything to the centered situation, but in general we are interested in such a moment when the guys are not centered, and we would like to have directly a formula for this. Okay, and these formulas, in principle they are formulas, but they are hard to understand. So the question is, what is the German case? Okay, that's something which we have to understand better. And of course we have seen some examples, and in these examples we have essentially two situations. I mean, there are situations where we have a quite easy formula. So namely there are joint moments for which we have easy formulas which are just a factorization. So they are easy factorization formulas. And I mean the main example for this is that if I consider phi of A1, B of A2, where the A's are free from the B's, then this factorized in a way which we know from classical independent variables. So maybe this is the same as phi of A1 times A2 times phi of B. Okay, so this is the case when the A's are free from B. So this is an easy formula. This is something which, okay, which you can understand quite directly. This is also the same formula as we would have for classical independent variables. But then we have more complicated formulas, where the structure is not so clear. So we have complicated formulas, where it's not that we just have a factorization in one term, which just factorizes, but we have a sum of terms, and they are more complicated factorizations. The typical example of this is this A1, B1, A2, B2, which is not just factorizing into phi of A1, A2 times phi of B1, B2, as we would have it for classical independent random variables, but we are getting here a sum of three terms, and each of them is a product of moments. Okay, so namely what we get here is phi of A1, A2, times phi of B1, phi of B2, plus phi of A1, phi of A2, phi of B1, B2, minus the product of the four moments. Phi of A1, phi of A2, plus phi of B1, phi of B2. Oh. Okay, and this is, I mean, those are the formulas which we have to understand better. Okay, but maybe before we try to get a better understanding for this, maybe we should look on the first one, because, I mean, this is a simple formula, and what is the difference between this and this situation? So why do we have something simple here, something complicated here, and in this case, we have here a moment, a mixed moment, which is in a kind of a nested structure. So what we have here, phi of A1, B, A2, this algebra where the B belongs to, is somehow this moment nested in the algebra where the A's belong to. So if I draw this pictorially, I get a picture like this, which means this element here is nested inside, sitting inside in a very nice way. And if you're looking here, I mean, here the elements, the A's are coming from algebra and these are coming from algebra, and they are not nested inside each other. Okay. So it seems that if this was something like this, we get nicer formulas. And actually, this here, this nesting, this can be repeated. So we can look on more general situations where we essentially iterate this and where we also get factorization. Okay, so maybe let us first look on this. I mean, those are the formulas which are easy to understand. So maybe let us try to see more what kind of formulas we have. But of course, in the end, we also should try to understand this. Okay, so first let's look on this nesting, and actually we can iterate this. Okay, so maybe, yeah. Here, so note situation 1, this formula in 1, this has a nested structure in the distribution of its algebras. So maybe they are sitting like this inside each other, and actually this nesting, this can be iterated to more complicated situations of the same type. This can be still nested situations. Okay, so let us look at an example of this. So for example, let me take more variables which are free. So let's say I have A1, A2, A3. Then I have some B variables, B1 and B2. And I have also C and D. And I assume that those variables are free. So this means the unitary subalgebra generated by the A's, the unitary subalgebra generated by the B's, the unitary subalgebra generated by the C, and the unitary subalgebra by the D. So those are 4 subalgebras, they are free. Okay, so assume those are free. And then let us look on the moment, let's say, of this form. B1, B1, C, B2, A2, D, A2. So this is now a joint moment in the variables which I have there. But if I draw again this picture, which shows me which elements are coming from the same algebra, so then C is free from the other guys, D is free from the other guys, but here I have the B's, so they are coming from the same algebra, and I have the A's. They also belong together. So I'm connecting the elements coming from the same algebra, from the free algebras, and you see again, I have here again a picture where I have this kind of nested structure. That some of the variables are just sitting inside the others in this very nice way. Okay, and so this is somehow iteration of this situation, and I can, for this, calculating this moment, I can use iteration of this factorization. So if I want to calculate this, I can reduce this essentially to this situation by just grouping things together. So for example, I mean, if I take this guy, then this is nested inside those elements in the same way as before. So I can write this, let's say, as phi of B1, and then I put B1, C, B2 together, and I put here A2, D, and A3 together. To make it clear, maybe let me also give new names to this. Let me call this A1 twiddle, let me call this B twiddle, and let me call this A2 twiddle. And then you see what I have here is actually now something, A1 twiddle, B twiddle, A2 twiddle, which is exactly of this form. And of course we also have the same condition which we need for using this factorization, namely that those guys are free from this guy. So I have here actually A1 twiddle and A2 twiddle and B twiddle are free. And why is this? Yeah, just because I mean the A twiddles here are just some function of the other variables which are free. So of course, I mean the A twiddles, they are functions of A1, A2, A3, and they also include the D, because I mean this guy is the D. So this, the algebra generated by this, is in the algebra generated by this, and the B twiddle, this is an algebra which is generated by B1, B2, and C. Okay, and those guys are free because essentially we assume that the A's, the D's, the B's, and the C's are free, and actually in one assignment we saw that. I mean, I have this kind of associativity, I can group things together. So I mean, this is the easy direction. So if the A's, the B's, the C's, and the D's are free, then I can also take the A's and the D together, and the B and the C together, and then those two guys are still free. This is quite easy. Okay, so this means those guys are free, and then I have for this, I have this factorization rule. So I have 5 A1 twiddle, A2 twiddle, times 5 of D twiddle. Okay, right, now back again, what this twiddled variables means. So this is now the same as 5 of, so the A1 is just, A1 twiddle is just A1, and A2 twiddle is A2, D, A3, and B twiddle is B1, C, B2. so you see we have essentially reduced this structure here now to a structure. I'm left with this and with this. So essentially I have to move this inner part here and factorize it. And now still, I'm not at the end because now I still have variables which are free, but now I can continue. So I mean this directly factorizes into phi of B1, B2, phi of C. And here, of course, I can group this guy together. And then I mean this and this is free from this, and it also factorizes in the same way into phi of A1, A2, A3 times phi of P. Good. Okay, and so you see that for such a joint moment, which has this kind of nested structure for the elements appearing there, it factorizes just in the same way as this example, or as for classical random variables. Well, if the A's and B's and C's and D's would be classical independent random variables, then we would have exactly this factorization rule. And that's exactly what we get here. So this means that we have joint moments which are of a specific form, namely those, and for them the calculation of the mixed moments is easy. They just factorize in the usual way. So this is easy to understand. Of course, we also have terms like this which don't factorize in this way. And of course, now I mean this 2, this equation 2, this has not this nested structure. So it means the elements from one algebra are not sitting in a nice way inside the elements from the other algebra, but what I have here is a kind of crossing between the two algebras. So this is not nested, but it is crossing. It should be obvious. I mean, what I mean is this. So I have A1, B1, A2, B2, and I mean the A's are coming from one algebra, and the B's are coming from one algebra, but I have none of them is sitting inside the other, but I have this crossing between the two algebras. And in this situation, it seems we have complicated formulas. And we have to understand the structure of this formula. So this means here I have a crossing term, and then I get here contributions, which we still don't understand, but maybe you might observe that actually the terms which I have on this side are still of this nested structure. So then let me write maybe this formula in a little bit different way, which maybe makes this clearer. So namely, what we have is phi of A1, B1, A2, B2. So this is phi of A1, but now phi of B1, maybe I write it here at this position where it actually belongs. A1, B1, A2, phi of B2. So this is the same as before. Phi of B1 is just a number, so I can move it out if I like, but I can also move it inside there. I just want to keep A1, B1, A2, B2 the order, because then maybe the structure becomes clearer. The second term I'm writing as phi of A1, phi of B1, phi of A2, phi of B2. So again, this phi of A1, I have written it here inside this phi, but again, it's just a number, so I can move it out. So it's just the same as the factorization. And then I have phi of A1, phi of B1, phi of A2, phi of B2. And now you see, I mean, essentially, the terms appearing here, they are related to moments, which again have this nested structure. So here, I mean, I have the B1, here I have the A1, B2, and here I have the B2. So you see, I mean, here the B1 and the B2, they are not connected, because I take the moment of B1 and the moment of B2. Okay, so this term here, I mean, I have here the B1 and the B2, they are the same phi, and the A2 and the A1, and get their separate phis. And here I have the product of four moments. So you see, we have here a formula here on this side. We have contributions which again corresponds somehow to this nested contributions. Nested contributions, which in a sense are somehow smaller than the non-nested or the crossing contribution which I have on this side. Okay, so this gives us a first hint that the structure of the formula has something to do with looking on this non-nested or this non-crossing partitions. Okay, before we go further in this direction, maybe we should make this more precise. Really make those pictures more precise. So what I have here, if I draw these pictures, I'm encoding the information which elements in my product are coming from the same algebra. And so what this formally is a decomposition of the positions. So some positions correspond to the same algebra, and I'm decomposing the position 1, 2, 3, 4, like the product of 4 terms. Those positions I decompose into subsets which tell me which elements are coming from the same algebra. And such a thing is called a partition of the set 1, 2, 3, 4. And so maybe we should now give more precise definitions and also notations to this, and then hopefully we can understand or describe these formulas in a more precise way. Okay, so let us now make some definitions and notations, and the crucial is of course this partition, and then the ones which have this nested structure. So officially they are called non-crossing partitions because they don't have this crossing. Good. Okay, so this definition 2.2. So let us consider the set. So just to argue, what we usually take partitions of the positions of elements, which means partition of the set 1, 2, 3 up to 4. But we could also do it in general. So we just take an ordered set. Let me move by S. So S should be finite. Let's say totally ordered set. So essentially, this is the same as 1, 2, 3, 4 up to n. Okay, and then we look on a partition of this set. So usually I denote this by pi. And what is this? So this is a decomposition of my set S into a disjoint union of non-empty subsets. Okay, those subsets usually I denote by V1 up to VR. So there are of them. These are of course open. I call this a partition, or maybe more precisely, partition of a set. So there are also partitions of numbers. No, but this is something different. Here we are really talking about partitions of sets. So this is a partition of the set S. If what I said, this is a decomposition of S into disjoint union of non-empty subsets. So let me write it down. So at first, the VIs are subsets of S. They should not be zero, and not the empty set. All of them. Then they should be disjoint. So I and J should be disjoint. I is different from J. And then, of course, together they should give me the whole set. Also their union, V1, union V2, and so on, union R. The union of all of them should be the whole set. Okay, so this is just such a decomposition. And the VIs, components in this decomposition are of course important, so we give a name to them. We usually call them the blocks of the partition. So, nice. Are called blocks. Pi. And if we want to know the number of the blocks, so this is R in this case, we also denote this by this symbol. So that's the number. That's the number of the blocks in pi. Which of course in this case is just R. this denotes blocks in pi. Good. So this is partition, and of course a partition is a decomposition, so it's actually equivalence relation on my set S. It tells me which elements are, it gives me the equivalence classes for elements. So we can also use this. To denote the situation that if I have two numbers in S, they are either the same block or not. And we write this as a P similar to this pi for Q. This is just a notation for the fact that P and Q are in the same block. This is just a notation that we have a kind of equivalence relation. So pi, you can also see pi as an equivalence relation. Okay, so Q. Same block of pi. Good. Then it's good to have a notation for the partitions of a given set. So usually we denote this by P of S, PS. So this is all pi's which are partitions of S. Good. And then usually our set S is just the natural numbers from 1 up to n. And then I just denote this by P of n. So P of n, this is just the shorthand for P of the set up to n. That's okay again. Set. Good. Okay, but then we have seen, this is general partitions, but there are special partitions which seem to be particularly important in free probability theory, namely those one. Those one compared to this. And this is a partition which we call crossing, because in this pictorial language we have crossing, and those are called non-crossing. So let's formalize also this. So the non-crossing partition are really the crucial ones in free probability. And in order to define non-crossing, so we say non-crossing is that it's not crossing. So essentially we have to define what does it mean to be crossing. And crossing in this picture means that I have two blocks which have this crossing. Okay, so crossing means I find at least two blocks which have a crossing, and non-crossing means that just such a situation doesn't happen. Okay, so let us define crossing, partition of the set S. Crossing. If we have two different blocks which cross, and what does this mean precisely? This means I have exactly this situation appearing for those two blocks. So this means if there exist, let's say, numbers Q1 smaller than Q1 smaller than Q2 smaller Q2 smaller than Q2 such that, and all those guys should be in S, such that the P's are in one block and the Q's are in a block. But those two blocks are different. So such that P1 is in the same block as P2, that Q1 is in the same block as Q2, but those two blocks are different, so this means P1 is not in the same block as Q1. And so we exactly have this situation that the numbers 1 up to n, I have the numbers 1 up to n, and somewhere I have the P1, then I have the Q1, then I have the P2, and then I have the P2, somewhere at the end. Of course, P1 might be 1, or P2 might be n. And we have the situation that those two guys are in one block. This block might be bigger, it might contain other elements, but we don't care about this. And the Q1 and the Q2 are in the same block. Okay, and then of course, if the numbers are ordered like this, I have crossing between those two blocks. And here, of course, you see that the order of S is now important. I mean, for just talking about partitions, I don't need any order on my set. Okay, it only becomes important if I'm talking about non-crossing, because this is non-crossing with respect to the order. And I have to say what does it mean that P1 is smaller than Q1, Q1 is smaller than P2, and so on. Good. Okay, but on the natural numbers, of course, I have the natural whatever. Good, so these are crossing partitions, and the partition which is not crossing, we will call it non-crossing. So this means it does not happen. I mean, whenever I take a pair of blocks, they don't cross. Is not crossing, then we call it non-crossing. It is called non-crossing. Good. And those are the important ones, so we should also have a notation for the non-crossing partitions, and we denote them by NC. So NC, S, by definition, the partitions of S, which are non-crossing. And again, maybe the most important S, this is the numbers 1 up to n. Of course, we denote this by NCN. So NCN, this is the same as the non-crossing partitions to set 1 up to n. Okay, and maybe some remarks and maybe also examples. Because we have seen some examples of, let's say, crossing and non-crossing partitions. Also the typical and maybe the smallest possible crossing partition is this one. So it's a partition of 1, 2, 3, 4. So this is in P4. It's a partition of the numbers 1, 2, 3, 4, and this is a crossing one. Okay, and then maybe typical, for example, for non-crossing one is, for example, let's say something like this. I have 1, 2, 3, 4, 5, 6, 7. So partition of 7 elements, and this is the partition which we had before for this nested join moment. So this is this one. So this is a non-crossing partition. This is first a partition of 7 elements, or of the set 1 up to 7, but it's actually non-crossing, because you don't find any two blocks which have this behavior. So this is 7. Of course, this means it's non-crossing. Yeah. And maybe before I talked, when we talked about this factorization of these special moments, then I also talked about nested. And maybe, nested and non-crossing is the same. This hopefully is clear, but maybe we should say it a bit more precisely. So here I talk about nested, but of course this is the same as non-crossing. And what does this nested mean? What did I mean with this? Of course, with this I mean somehow that you find in your partition, that you find a block which essentially is nested in the other one and you can take it out. And this means that this block only consists of neighbors. If you have such a block, you take it out, and then again you remain with the non-crossing partition, so that you then can take out another of those blocks and continue until nothing is left. And if you have a crossing partition, this is not possible. You might be able to take out a few blocks, but at some point you will remain with a situation where this is not possible anymore. Formalize this a bit. I'm saying it is easy to see that this non-crossing is actually the same as what I called nested before. It's the same. It's nested. And what do I mean with this? So this means, so I, a partition of 1 up to n, is non-crossing, it's nested in the sense if I find a special block, which I call an interval, which just consists of neighbors, and if I take out this block, then I'm left with another non-crossing partition. So this means I have a recursive way of dealing with non-crossing partition. And that's usually in applications and proofs, and so they're very useful. That's how you usually use the property that something is non-crossing. So this means I find a block in my partition, which is special, so it is an interval. So this means it really consists of neighbors. And if I remove this, and then I get a partition of the remaining numbers, and this is then still non-crossing. Okay, so maybe make this precise. So this means this V being interval means that it consists of just of neighbors. So it starts with some k, when it is k plus 1, and it goes on k plus 2 up to some k plus 3. Where those are just neighboring numbers, where k, so I mean, of course, this is a subset of 1 up to n, and this p can also be 0. So it can just consist of k, or it can be k and k plus 1, and p is 1, and so on. So this means for some k equal to n, some p greater or equal to 0, such that of course k plus p is still less than n. Okay, so this is an interval, so I have to find such a block, and then if I take out this block, then I'm remaining with p without this v, and this should be then a non-crossing partition, so this one block is removed, so also those numbers are now removed, and then I'm left with the remaining numbers, and this guy should then be a non-crossing partition of those remaining numbers. So this should be non-crossing partition 1 up to k minus 1, and then those numbers are missing, and then I'm continuing with k plus p plus 1 up to n. And of course, essentially, this is as often non-crossing partitions from 1 up to n minus p plus 1. I could rename the numbers here. 1 up to k minus 1, then I would go as k, and going on up to n minus p plus 1. So usually we will do this identification stuff between non-crossing partitions of various sets. So this is the same as non-crossing partitions of n minus p plus 1. Good, but this means I do a nice step, and then I'm back to a non-crossing partition of something smaller, which means I can repeat this. So of course at the end I should be able to remove everything. So this means that I can essentially reduce a non-crossing partition by this kind of successive interval stripping, taking out intervals, to nothing. And that's another equivalent characterization of non-crossing partitions, and this is very useful in concrete applications for proving things. Okay, so maybe and maybe also do an example. This one. Yeah, okay. So we write this down. So what this means here, I can iterate this. So what this means, you can reduce the non-crossing partition by doing this successively. So by successive, and this removal of interval, and also called interval stripping, I can reduce my partition to just the empty set. So I can remove everything. I can take away all the blocks. Just an example, just to make sure that you all agree what I'm claiming here. So let us take this example which I had before. So this was 1, 2, 3, 4, 5, 6, 7. So non-crossing partition of those 7 elements. I have this 3 and 6 are blocked on its own. Then 2 and 4 are in a block, and 1, 5, and 7 are in a block. Okay. And here, of course, where are the intervals? I mean, here's an interval. So this is an interval of one element, and here's another interval. Of course, it is, I mean, 2 and 4. I mean, this block is not an interval because it doesn't consist of consecutive guys. Okay, but this is a neighbor and this is a neighbor, so I can take them out. So I take them out, all of them. So I remove the intervals. Intervals should consist of 3. I remove the block 3 and also the block 56. And then I'm left with 1, 2, 4, 5, 7, and I'm left with this. And now this is a non-crossing partition of those 5 guys. I mean, I could rename those guys now 1, 2, 3, 4, 5, but maybe it's better to leave it like this so that it's clearer how it corresponds to the original one. And now, of course, I have now new interval. I mean, 2, 4, which was not interval here, has now become interval. So now I mean, those are consecutive elements. So I can now remove this guy. I can remove now the block or the interval, the block which has elements 2 and 4. And if I do this, I'm left just with 1, 5, 7. And this is now just one block which is also an interval. 1, 5, and 7 are now consecutive elements. Okay, I can remove this. And then I just end up with nothing, the empty set. Yeah, but now of course, I mean, why are we interested in such partitions, or where do they come up? I mean, they came up when we looked on how do I factorize, what are the rules for calculating moments of joint elements. And I mean, with those pictures or partitions, somehow I indicated the positions of elements coming from the same algebra. So where those partitions show up are essentially when I have an index set or an indexing set, which tells me where my elements in the product are coming from. So actually, this is the next definition. The partitions which come up in our context are usually partitions coming from index tuples. So let's say I have a multi-index. Let's say I, so this is I1 up to ik. So this usually comes from the situation that I'm looking on a product, A1 up to ik, and the elements aj are coming from one of the algebras. And here I'm recording from which algebra they are coming. So this is a k-tuple. So I1 is the algebra from which the first element comes, I2 is the element from which the second element comes, and so on. Okay, so that's the crucial information. So here, such a multi-index, k is here a natural number, and of course the I1 and the IK are coming from our general index set, I. And And such a multi-index, it might also be nice, and we can also do this in the following very often, of course, can be considered or actually is the function. I mean, I have already written it more or less as a function here. I could, of course, also write it with sub-indices, I sub 1, I sub k, but I mean, I write it like this for better legibility, but also because it actually is a function. So I mean, I can also consider this. Considered as a function, so I maps the interval 1 up to k. So usually I denote this, so this is a notation for this interval, so it's a function from there up to I. So where this k is just denoting the set 1 up to a. So the first n natural numbers. Okay, and for such a multi-index or function, we define this kernel. That's the position which tells me where the indices are the same and where they are different. That's what I want. That's what we call the kernel, and this is a partition of 1 up to k. For such a multi-index function, I for k I, we define a partition. And we call it the kernel of I. We define this kernel. And usually we use the notation ker I. So this is a partition of the numbers 1 up to k. Those are those numbers. And it's essentially the Greek images of this function of the various elements showing up here. Or another way, it says, I mean, two elements are in the same block if the I value at those positions agrees. For definition, so P and Q with respect to this partition, with respect to this kernel, are in the same block if the function P, I of P, has the same value as the function Q. So you can say, I mean, the blocks are the pre-images of the values which this function can take on. And of course you're forgetting about the empty sets. Okay, so this means this kernel really, I mean, this encodes the information where the values here are the same and where they are different. And that's the crucial information which we need for doing things. Okay, so let me do an example. Here. What I mean here. So let me, for example, consider the following multi-index. So I, so it's a, let's say k is 7 in this case, and I is, let's say, 1, 2, 3, 2, 1, 4, and 1. So this means I of 1 is 1, I of 2 is 2, I of 3 is 3, I of 4 is 2, and so on. And of course, also this is, in our situation, this would correspond to the situation where we consider a product of 7 elements. The first element comes from the first algebra, the second from the second algebra, the third from the third algebra, and then the fourth comes again from the second algebra, the next from the first algebra, from the fourth algebra, and from the first algebra. So this is this information. But what is really relevant of this information is where those indices are the same and where they are different. So this means where elements are coming from the same algebra and where they are coming from different algebras. So this means what is the kernel of this? I just have exactly two tutorial pictures as before. I mean, I have to connect the elements which are the same. So this 2 shows up here and here. I mean, 3 is alone, 4 is alone, and 1 appears here and here and here. So this is exactly the same situation as we had before. So this means the kernel of this multi-index is this partition here. kernel of I, for this specific I, is this partition. So very often I draw partition in this graphical way. Of course, formally, it's a collection of blocks, and the blocks are the positions which are the same. So I mean, it's a partition of 1, 2, 3, 4, 5, 6, 7. It tells me at which positions the i's are the same. So this is the position 1, 5, and 7. So this is this, and this. Then the position 2 and 4. And then the position 3 and the position 6, they are block of its own. They only appear once. So this is and 6. And of course, this is a non-crossing partition of 7 elements. And of course, I mean, there are many multi-indices which have the same kernel. Because I mean, I'm recording only very specific information about this multi-index. Multi-index, really, I mean, this tells me exactly the algebra which appears at this position. But what I'm really interested in, what is really relevant, is just the information where the algebras are the same and where are they different. So it means, for example, if I take another multi-index which has the same kernel, for example, is let's say 8, 3, 4, 3, 8, 1, and 8. So this again, 4 appears only here, 1 appears only here, 3 appears twice here and here, and 8 appears here, here, and here. So you see this is the same partition as here. Also the kernel of this is the same as this kernel. Good. Okay, so I hope this is clear. And of course, we also have multi-indices where the kernel is crossing. So the basic example of this is, of course, you have a multi-index of 4, that's 4, let's say 1, 2, 1, 2. Corresponding to the situation, I have a product of 4 elements. The first comes from the first algebra, the second from the second algebra, the next one from the first algebra, and the last comes again from the second algebra. So the kernel of this, of course, is this basic crossing partition. So this is a partition of 4 elements, but it is crossing. And those, so if you're looking on a product of elements and the kernel of the index set is crossing, that's the ones which are really tricky, which we have to understand. Good. Okay, and maybe now, maybe in this language, maybe we can formulate again what we have seen before, namely that at least for non-crossing, if the kernel of our indexing set is non-crossing, then we have a nice factorization. Okay, so let's again do what we already know. Of course, at some point we have to go to the crossing ones, but let us formulate first the non-crossing ones, because there we understand quite well what is going on, and now formulate a little bit in this language. So I believe. Yeah, so this is the remark, which puts all this now together with our problem of calculating joint moments of free random variables. Yeah. So what is the set? So again, we have a non-commutative probability space A phi, and we have 3 subalgebras. What we want to know is what is a mixed moment, a joint moment in elements coming from those subalgebras. So what we consider is the product in 1 to k, where k is a natural number. And each of these factors here, each ij, is coming from one of the subalgebras. So say from the ij subalgebra. Good. Okay. And then somehow it seems to be, I mean, the crucial relevant information is now actually the kernel of this multi-index I. So I is now multi-index. So we have I1 up to I of k. This tells us where the elements are coming from the same and where they are coming from different algebras. And it seems to be relevant whether the kernel is crossing or not. Whether we have a nice or not a nice formula. Okay, so, and what we know, what we have seen, is what happens in the case where the kernel is non-crossing. So, if this I is multi-index, of course, is now is I1 up to k. This tells us from which algebras our elements are coming. And if we assume, or if we have a situation, that this kernel is a non-crossing partition, so this kernel in general is just a partition of k elements, but it could be a non-crossing partition, and then actually we have seen that we have then a very nice factorization. Also assume this kernel is non-crossing, then we have seen at the beginning today, first calculations which we did, that, let me write the kernel, let me write down explicitly the blocks, so it has number of blocks, let's say R blocks, and we know them 1 up to dr, and then I can write this joint moment of 1 up to k, so this actually factorizes into a product of moments, and I have a moment for each block in my partition. So maybe all the elements which are coming from the same algebras are just multiplied together and I take 5 of them. That was really what was happening there. So what I have here is a product of moments, and for each block of my non-crossing partition I have 1 5. So maybe I take 5 and I'm multiplying all elements together which belong to the first block. So all elements which come from the same algebra are getting multiplied together, and of course things don't commute, so I should say in which order do I multiply them, and of course I multiply them in the same order as they appear here. So maybe I denote this by this arrow. So this should say that I keep the order which I have here. So I multiply all the ALs for which IL is in the block E1. And so I multiply all elements which are in this correspond to this block. Then I do the same for all elements in the second block and so on, up to all elements in the last block. So again, I take the product in the original order of all elements, so the product of all L, such that I of L is in ER. Good. Okay, is this the correct way of writing it? I'm not sure at the moment. So I take, so the V's are the positions. So the V's actually tell me the positions where I should multiply. So actually I should multiply here over all L in the RB1. So I multiply over all L in B1, and then the partitions of the positions. Okay, here also I multiply over all positions which correspond to the last one, so over all L in VR. Which means, of course, that I'm multiplying over all guys which have the same I of L. But I don't specify what's the value of I of L. Good. Okay, so I maybe also did this product sign with the arrow on top. So this says that I take the product and I take the product of some elements, but I take those in the original order. So product of vectors in the same order as in the original product, as in A1 to AK. And actually, for this formula, we don't really need that neighbors are coming from different algebras. So you can always reduce things that neighbors are coming from different algebras, but I mean for this factorization, we actually don't need this. So maybe let us just look again at an example. I mean this factorization which we had before, just write it down in this language. Then you really should go over the direction of understanding more. At the moment I'm still talking about the simple factorization. But of course, the real goal will be to understand the other things. Good, but these are the ones which you understand, the ones where the kernel is non-crossing. And so maybe let us look on the example A1, A2, A3. Let's say they are in some algebra M1. We have B1 and B2. So this is the example which I had before with the A's, B's, C's, and D's. Let's say the B's are in the algebra M3. The C is in the algebra M7. And the D is in the algebra A2. So I have a couple of algebras which are free. And I take out some elements out of them. And what I consider was this product A1, B1, C, B2, A2, D, A3. No? And then of course the kernel of this, I mean A1, A2, A3 is in the same algebra, B1, B2 is in the same algebra, C is an algebra of its own, and D is also an algebra. So the kernel of this is this. And of course, first the index set. The index set I here is of course, I mean, this comes from the first algebra, this comes from the third algebra, this comes from the seventh algebra, third algebra, the index coming from, no, B comes from the third, then I'm coming again from the first, D comes from the second algebra, and the A comes from the first algebra. So that's my index set. But again, the kernel is just given by we are connecting the same numbers. So this kernel is really this picture, and this is, I mean, was a non-crossing partition of 7 elements, and for this, for such a situation, we know that phi applied to this factorizes according to the block structure. So what we have phi A1, B1, C, B2, A2, B, A3, which corresponds to this. This factorizes into a product of terms. We have a vector for each block, and in such a vector we just multiply the elements corresponding to the block together and take phi. So what I get is for this block, I take phi, and then I multiply the elements corresponding to this in the original order. So I take A1 times A2 times A3. That's what I mean with this arrow. Okay? Taking the original order. So A1, A2, A3. Then I have the B's. So I have a block here corresponding to the B's, which are elements in the algebra A3. And so I get multiply B1 B2. Okay, and then also have the C and the D, a block of its own, each of them, so it's just phi of C times phi of D. So that's just what this formula here means. And we have seen at the beginning, I mean, for every non-crossing partition, it's just iterating this factorization rule for this situation. Well, that this factorizes into phi of a1 times a2 times phi of b. And if you iterate this, and I mean for non-crossing partitions, you can iterate it always just using this. You get exactly this factorization, as we have seen at the beginning of this example. Good. Okay, but now of course the question is what happens if our kernel is crossing? Then the structure of the formulas is more complicated. So if the kernel of I is crossing, then yeah, what? So what is the structure of the formula? We don't have a good idea of what this is. Good. Okay, and in order to get an idea how we can describe such general situations, and maybe what is the structure in the background, I will now look first on maybe a basic theorem in free probability theory, one of the first, namely as a free central limit theorem. Or maybe I will also look on more general limit theorems, because they tell us somehow the structure of mixed moments. How a good way of dealing with them. And so in particular, I will now talk about the free central limit theorem, which was one of the first results of Regulescu in free probability theory. But I will also contrast it with the classical central limit theorem, so that we really see that we are doing a free analog of a classical object. And actually, I will prove both at the same time, just also to get some idea in which sense freeness and independence are somehow the same structure. So we see somehow the similarities between classical and free, but we also see the differences. Okay. So, and for this, let me first formulate the two central limit theorems, and then I will give you a proof. And that it will be a kind of combinatorial proof, which makes contact with this notion of partitions and such things. Good. So let me first give you the formulation of the classical central limit theorem. And of course I formulate it in algebraic language. I mean in our notation, where we are not talking about classical probability spaces, but we are talking about non-commutative probability spaces. So we have our algebras and our expectations. So in particular, this means in this algebraic setting, I can only talk about classical random variables for which all moments exist. Because I mean, we apply our expectation to everything in our algebra, and this should exist. So we are not in this language we cannot deal with the most general situation where maybe only a few moments exist. But I mean, it's good enough for us. So let me recall the classical central limit theorem. This is one of the more basic theorems of classical probability theory. Central limit theorem. So what is the setting? Of course, I still take the setting of having a non-commutative probability space, but actually then the algebra will be the algebra of classical random variables, which is commutative. But I mean, our non-commutative probability spaces might also be commutative algebras, but that's okay. But let me just formulate in our general setting, so using the same language for classical and free situations. So A phi should be a non-commutative probability space. And now I consider random variables, AI, in A, indexed by I. And now I really want infinitely many. Because the central limit theorem is about the sum of independent random variables. I mean, the sum bigger and bigger and bigger, and I normalize it by square root of n. And then I ask, does this converge to anything? And of course, in the classical context, it converges to the normal distribution. Okay, so I have those random variables, and I assume now they should be classically independent. So I assume I have random variables which should be classically independent random variables, and we more or less talked about this, but maybe let me write it down again what this means. Classically independent random variables. So first of all, I mean, in the classical context, random variables commute, so I assume that all the A's commute among themselves. So I and J commute when I different from J. And of course also I equal to J. Good. Okay, so they commute, and then I have a factorization rule for any mixed moment. And in the classical setting, because things commute, any mixed moment, any joint moment, in those A's, can be brought in a form that I have, let's say, a power of A1, then I have a power of A2, a power of A3, and so on. I mean, that I have A1, A2, A1, A2, I can bring this in the form A1 squared, A2 squared. So I can always order my variables. So the only thing which I really have to say is what is A of, let's say, I1 to some power R1 times A of I2 to some power R2, and so on. Find the product up to, let's say, IK up to RK. And I can restrict to the case where this ICR increasing. So let's say I have a power of A1, I have a power of A2, maybe the power is 0, then I don't have it. So maybe I just have A1 to the power 4 times A5 to the power 7 times A9 to the power 2, something like this. But I can always commute things, so I can assume that the indices here are strictly increasing. Okay, this means the I1 does not show up again here. Okay, and then I just have the factorization. Such a product factorizes with phi of this times phi of this and so on times phi of this. This is just a classical independence. And of course it's the same as our factorization rule if the elements are ordered like this. Because this is still a non-crossing partition. But in non-commutative, of course, I need much more joint elements. In the classical case, everything can be called in this form, and I have this factorization. E of I1 power R1 times phi of A2 power R2 and so on, phi of AJK power RK. For all indices where I1 is strictly less than I2, strictly less than I3, and so on, strictly less than IK. And those powers here are natural numbers. Of course, they could be 0, but then I just omit this item. So if you like, you could also say I have 1, 2, 3, 4, and so on, and then I can also allow some powers in future 0. But there I can anyhow, so here 1 to k should be natural numbers.
But then I now need the index set to be ordered in some way, or I mean, before we didn't have that.
I mean, my index set is ordered. I mean, these are just this index set is of course ordered. I mean, I have algebra A1, algebra A2.
Okay.
No, actually, I mean. Yeah, okay, this index set should be ordered. And always, this index set is just a subset of natural numbers. In this case, it will just be the natural numbers themselves. Huh? So I just have a sequence A1, A2, A3, and so on, infinitely many. Also, these I are just the natural numbers. Yeah. Okay, so this is the assumption that I have a sequence of independent random variables, and now in the central limit theorem, we make a few assumptions about the distribution. So, first of all, I assume that my random variables are identically distributed. This can be weakened, but this is the simplest situation which makes the proof also. Yeah, so So I assume that first of all my variables have the same distribution. So I assume furthermore, so all AI are identically distributed. Also, this means I have here a sequence of IID random variables, independent and identically distributed. And identically distributed just means that all their moments are the same. So this means that if I'm looking on the variable AI and the variable AJ, they have the same distribution, but distribution for us is just a collection of moments. So this means if I take the arc moment of AI and the arc moment of AJ, they are the same. Right? This has to be true for all powers R, for all moments, and of course also for all AJ. Good, so this means my random variables are independent and identically distributed, but then of course in the central limit theorem you need a few more assumptions about distribution, and the crucial one is that they are centered. So the first moment is 0, because otherwise you would first look on the law of large numbers. So we assume now that the first moment is equal to 0. And of course, because of their identical distributions, means the first moments of all of them are the same. So it means it's enough essentially to ask that one of them is centered, but this means all of them are centered. And then for the second moment, we take some normalization. The second moment, of course, or the variance in this case then, is not 0, but so we normalize it and we ask that it is equal to 1. This is more normalization. So phi of a squared is equal to 1. Okay, and about the higher moments, there are no assumptions. Of course, they exist in our frame, because phi is a linear function on our algebra. The algebra contains all the powers of the variables, so phi must be defined there. In classical probability theory, you can also talk about random variables for which not necessarily all moments exist. But this doesn't fit in this frame. But anyway, this frame is still not good. And so what am I now interested in the central limit theorem? I'm looking on the sums of my variables. So I'm taking the sum, then we call it Sn. So there I'm summing the first n variables, and then I need some normalization if I want to ensure that for n going to infinity, I have a kind of convergence. So I take the sum, a1, plus and so on, up to an, and then it turns out I have to normalize this by the square root of n. And the question is, does this converge to anything interesting, meaningful in the limit n going to infinity? And of course, the statement of the classical central limit theorem is that this really converges to the normal or the Gauss distribution. That's why the normal distribution is so important, because it's the limit in the central limit theorem. So then, Sn converges the normal variable. A normal sense of probability theory is a Gaussian variable. So it's a specific variable with a very specific distribution. So normal variable. Okay, what do I mean with convergence here? Of course, usually it's the convergence of distributions in a big sense. But in our algebraic setting, the only thing which we have are the moments of the variables. So what we really mean here is that the moments of Sn converge to the corresponding moment of the normal variable. So that's what this is saying here, and which is more or less equivalent to the other convergence distribution in classical probability theory. Okay. But we will come back to such more analytic questions later. So now we have a purely algebraic setting. And there the only meaningful notion of convergence is the convergence of moments. So in our algebraic setting, the statement is, if I take the limit n going to infinity of a moment of and let's say I take the kth moment, so I take Sn to the power k, but then I'm sending n to infinity, so the sum is getting bigger and bigger, and actually this converges to the corresponding kth moment of the normal distribution. And the normal distribution I can write down explicitly, so this is given by some normalization factor, and it lives on R from minus infinity to plus infinity. I take a kth moment, and the normal distribution has a density e to the minus t squared over 2. This is the normal distribution which has variance 1. That's essentially the variance coming from here. So this is the normal distribution which has mean 0 and variance 1. So you see that's the information which survives from our input. And the other moments here, they just disappear, but of course in the limit I will get the moments of the normal distribution. Okay, so this is the central limit theorem. And of course it will be good maybe to know what is actually the value of those moments, and it's, you can calculate this integral. You should do it at least once in your life, and it turns out that you really can write it down very explicitly. Actually, those moments are really just nice natural numbers. Of course, if k is odd, so this is an even distribution, then it is 0. For the odd situation, it is 0. But in the even situation, what you get is a kind of product of natural numbers. So namely, what you get, even k is k minus 1, k minus 3, and so on, up to 5 times 3 times 1. K is 9. So what you take is the product of the natural numbers starting at k minus 1, and then you're going down in steps of 2. You multiply with k minus 3, with k minus 5, and then you're going down, and because k minus 1 is odd, you will hit 5 in 1. And if k would be even, if you do this, then you will hit 0, and then you get 0, so it's also consistent with this. So we have here kind of factorial, but you are only taking the odd numbers. And I mean, there's also a notation. Usually this is denoted as k minus 1 double factorial. This double factorial, it doesn't mean that you take the factorial of the factorial, but it just means that you multiply things, but you go down in steps of 2. Good. Okay, so I mean, maybe you should calculate this. So, those are just the numbers which are coming out. So the statement of the classical central limit theorem is that the moments of our normalized sums here in the limit going to infinity converges to those concrete numbers here. And so that's what we should see. Good. Okay, and so Voiculescu did an analog of this. So it's clear, an analog now. And what is an analog of a classical theorem? Essentially, what you should do is you should replace independence by freeness. So we take somehow the same kind of assumptions. We take random variables, the sequence of random variables, but we do not assume that they are classically independent, but we assume that they are free. Then we are looking on the same, and we make the same assumptions about the mean and the second moment. And then we look on the same quantity. We are summing the first n variables, normalize it by n, and then we can ask what happens if n goes to infinity. And again, in our algebraic setting, the main question is the moments of this normalized sum, do they converge to something? In particular, do they converge to the moments of some probability measure? And it turns out that they do, and what we get there is the semicircle distribution. Okay, and again, the semicircle distribution can give concrete numbers for the moments. And I think I will stop for today. So next time I will write down the statement of the free central limit theorem, and then I will actually give a proof to you of both theorems, more or less at the same time. Because in this algebraic setting, and from a combinatorial point of view, I mean the proof is more or less the same, at least up to some point. Of Because at some point it's important whether you have classical independent or free independent variables. But many of the arguments which show you the structure of what you get in the end are the same. But so this will be done next time. So that's it.